Recently, we've been discussing the fact in class that for a vector space or a subspace of a vector space, an orthogonal basis is very convenient to work with. So the idea of this video is to discuss what's known as the Gram-Schmidt process. Suppose we start with a basis of vectors, W1 up through WK. It's a basis for Euclidean space, Rm, or some subspace of it. The idea of Gram-Schmidt is to first take these vectors and use orthogonal projections repeatedly to convert this basis to an orthogonal basis. And if we want to, we can then actually divide each of these vectors, v1 up through vk, they're all orthogonal to one another. We can divide each by its length and create what we know or what we call an orthonormal basis. An orthonormal basis is a basis where the vectors are orthogonal to one another and each has length 1. So the goal of the next few minutes is to discuss how to perform this process. Let's look at a simple example in R2. What I have here, two vectors, 1, 1 and 1, 2. I've drawn them here, W2 and W1. These are obviously a basis for R2. Now, the first step of the Gauss-Jordan elimination process always is to set, let's say your first vector is W1, is to set V1 equal to whatever W1 is. So in this case, V1 would actually be what you see here in W1 itself. Now, what we want is we want a vector that's perpendicular to W1. And a convenient vector to use would be this vector V2. This vector V2 has the property that if I draw the line through W1, this is perpendicular to that line. And we know from preceding discussions that if we take the projection of W2 onto W1 and subtract that projection from W2, we actually can get this vector right here. So in other words, V2 will be W2 minus the projection of W2 onto V1, which is W2, and then this projection is the same as the dot product of W2 with V1 divided by the length of V1 squared times the vector V1. This is just a scalar out in front. So let's go ahead and compute that quantity. W2 was 1, 2, and then we subtract the projection of W2 onto V1, and if we take the dot product of W2 with V1, V1 is W1, so if we take the dot product of these two vectors, we get 3, so that's where my 3 comes from. And if I take V1, which is W1, if I look at the square of its length, I get 2. So V2 would be 1/2 minus 3/2 the vector V1, which is 1, 1, and if we simplify that, we get minus 1/2, 1/2. So again, this vector is that. This scalar right here is this scalar right here simplified, and then we have the vector V1, which is the same as W1. Okay? Now we need to take these vectors and we need to normalize them to get an orthonormal basis. Well, U1 is pretty easy. If we take V1 and look at its length, it's root 2, so we get 1 over root 2, 1 over root 2. Now let's take a look at V2. We need to find the length of V2. Now that looks like it's going to involve lots of fractions, so here's a trick. We know that V2, which is minus 1/2, 1/2, has to be parallel to the vector minus 1, 1. So if we take this vector and normalize it, we can use that as U2. Well, this vector, when normalized, is minus 1 over root 2, 1 over root 2. So here's U2, here's U1. It's easy to check that the dot product of U1 with U2 is 0. So this is an example in 2 space. Let's take a look at an example in 3 space. So I have 3 vectors. 1, 0, negative 1, 2, 3, 0, negative 1, 2, negative 1. Now, these vectors When I put them into a matrix as column vectors and row reduce, I get the identity. So we know that those three vectors form a basis for R3 by the invertible matrix theorem. What we're going to do is we're going to use the Gram-Schmidt process now to create, starting with them to create an orthonormal basis for R3. So the first step is to let V1 be W1, which is 1, 0, negative 1. The next step, just like before, V2 is W2 minus the projection of W2 onto V1. Let's do that simple calculation. W2 is 330. If I take the dot product of W2 with V1, which is W1, let's take a look at W1. So I take the dot product of these two, I get 2. If I take the length of V1 squared, I get 2 as well. And I'm going to multiply that by the vector V1, which is 1, 0, negative 1. So this scalar right here corresponds to that scalar. Here's V1 down here, and here's W2. And when I simplify this, I get the vector 1, 3, 1. So we've calculated V2, 1, 3, 1. We know that V1 is 1, 0, negative 1. Let's go on and calculate V3. Now what we're going to do is we're going to look at the plane formed by our vectors V1 and V2. Okay, now V1 and V2, they are linearly independent and they're perpendicular. So I've drawn them like this, and their span is in fact a plane. Our third vector has to be perpendicular to both V1 and V2, so therefore our third vector, V3, is going to be in the orthogonal complement of W. Well, we've actually solved problems like that before. So what we're going to do is we're going to take V3 to be W3 minus the projection of the vector W3 onto the plane. So the idea is that the vector W3 might be pointed off like that. We're going to project it down onto the plane, which is capital W, and we're going to subtract that projection from W3, which is going to give us a vector that's perpendicular to the plane. So here are the vectors for reference. W3 is negative 1, 2, negative 1, V2, and V1 we calculated on the previous page. So W3 is going to be, V3 is going to be W3 minus the projection of W3 onto that plane W. Now this we know we can write as a linear combination using dot products from our previous discussions. W3 dot V1 over the length of V1 squared. This is all a scalar, which I multiply times V1. And I take W3 dotted with V2 divided by the length of V2 squared, multiply that by the vector V2. This is actually a multiplication sign here. So let's calculate that quantity. W3 is negative 2, negative 1, 2, negative 1. If I take the dot product of W3 with V1, that dot product is in fact 0. So all this stuff goes away. Let's take the dot product of W3 with V2. W3 and V2, the dot product, minus 1 times 1, 6. It's actually going to be 4. So that's where this comes from. Now we need to divide by the length of V2 squared. If we take 1 squared, add 3 squared, add 1 squared, that gives us 11. So we have an 11 here. And then we multiply that by V2, which is 1, 3, 1. So V3 is going to be this vector minus all of this, and through the modern conveniences of algebra, we get minus 15 elevenths, 10 elevenths, minus 15 elevenths. So now we have V1, V2, V3. We're going to normalize them to get an orthonormal basis. Okay, sorry about that. So here's V1, it's 1, 0, negative 1. It's pretty easy to see. If we normalize that, we get 1 over root 2, 0, minus 1 over root 2. V2 is 1, 3, 1. If we square each of these quantities and take the square root, we get square root of 11, so that says that U2 is 1 over root 11, 3 over root 11, and 1 over root 11. Now let's take a look at that third vector, V3, minus 15 elevenths, 10 elevenths, minus 15 elevenths. We don't want to calculate the length of this vector, but if we look at what's happening, this is actually vector parallel to minus 3, 2, minus 3. We could cancel the 11s out, 5 goes in, 3, 2, 3 times. So this vector is parallel to this, and this vector has a length of the square root of 22. 9 plus 9 plus 4 is 22. So that says that U3 would be minus 3 over root 22, 2 over root 22, minus 3 over root 22. So there is our orthonormal basis for R3, and it's fairly easy to check that, and we should do that. I'm not going to do it here, that each of those vectors are orthogonal to one another. One last example. 3 vectors in R4. W1, W2, W3. If I put these vectors into a matrix, that matrix is going to be 4 by 3. If I row reduce it, I get the following. Notice how I have a pivot in each column. This means that the vectors W1, W3, W1, W2, and W3 are linearly independent. They form a basis for the span of those 3 vectors. In other words, our subspace W is going to be the span of the 3 of them. This is a basis, but we're going to convert this to an orthonormal basis. It's a 3-dimensional subspace of R4. So let's get started with Gram-Schmidt. V1 is W1, which is 1, 1, negative 1, 1. V2 would be W2 minus the dot product of W2 with V1 over V1 squared, its length, dotted with V1. Now, if you take W2 and dot it with V1, you'll notice that you get negative 1. That's where this is coming from. And the length of V1 is 4. 1 squared plus 1 squared plus 1 squared plus 1 squared. Square that, you get 4. So here's W2 minus a minus 1/4. And then V1, which is W1, is right here. And if I simplify this, I get 5/4, 1/4, 3/4, minus 3/4. So that's V2. How do we get V3? We take W3 minus the dot product of W3 with V1 over the length of V1 squared times the vector V1. So this whole thing is a scalar, minus W3 dotted with V2 over the length of V2 squared times V2. So here's W3, 2, 1, 0, 1. If I take this dot product and compute it using the vectors, I get 4. The length of V1 squared is 4, and then this is V1, which we computed a few minutes ago. If I take the dot product of W3 and V2, where's W3 on this page? There's W3. There's V2. If I take the dot product of them, I'll have 10/4 plus 1/4. That would be 10/4 plus 1/4, 11/4, and then minus 3/4. I hope I'm looking at the right vectors, but in any event, the dot product, the dot product is 2, and the length of V2 squared is 11/4. Okay, I've left out a few calculations here, and here is V2, which we calculated above. If we simplify this whole thing, we in fact get 1 over 11 minus 2 over 11, 5 over 11, 6 over 11. There's a fair amount of fraction adding going on here, but I have checked this on a computer and I know that it works. So here's where we're at. V1 is that vector. We normalize it, we get 1/4, 1/4, minus 1/4, 1/4. Here's V2. 5/4, 1/4, 3/4, minus 3/4. Forget about the 4s for a moment. This is parallel to 5, 1, 3, negative 3, whose length is 2 over root 11. So we can take these entries, divide by 2 over root 11 to get our vector u2. That's the second vector in our orthonormal basis. And now we need our third vector. v3 from the previous page was given by this. Let's just ignore the 11s. This is parallel to 1, negative 2, 5, 6, whose norm is the square root of 66. So that says that u3 would be given by 1 over root 66 minus 2 over root 66, 5 over root 66, and 6 over root 66. Of course, we could simplify the radicals, but we don't need to. In any event, these three vectors form an orthonormal basis for W, which was a three-dimensional subspace of R4.